All right, we are now live streaming.
Awesome. Thanks a lot. So I would say let's just slowly start. Welcome everybody. This is the Zero Knowledge Learning Group, which is like a community meetup series by Linux Foundation Decentralized Trust. I'm Daniel, and I'm hosting this learning group for SNARK and Zero Knowledge application development and mostly programming. And the today's topic is like, on the one hand, we're gonna like a little bit like kick off this year because I mean it was a full event series last year, and I'm planning to do it this year as well. So I'm gonna kick off a little bit this year's plan. And on the other hand, we're gonna have a little bit like a little bit more theoretical topic, which is like STARK, scalable, transparent argument of knowledge. We're not gonna go deep into the math or any theoretical basis. What we're gonna do, we just compare a little bit like SNARK to STARK. What are the differences? What are the similarities, and so on. So that's the agenda. I'm gonna just start just in the next slide with the logistics of this whole learning group, and then coordination and stuff like that. Then we're gonna cover some of the technical content. So like I'm gonna like summarize the knowledge proofs as usual. Then I will continue with, again, the major idea is like comparing SNARK and STARK. We stay on a high level for the first run. So just like some high concepts, some algorithmic considerations, then the advantages and disadvantages of trusted setup. Then I'm gonna have like a high-level flow of zero-knowledge programming, some ideas on arithmetic circuits and arithmetic intermediate representation, like R, some ideas on constructions, on the differences and similarity of construction of SNARK and STARK. I mean, I would say it's like zoo of zero-knowledge proofs, so like different ideas of zero-knowledge proofs, some applications, and then we're gonna finish with links, resourcing, and Q&As. So that's actually the plan for today. So basically, let me just start with the like most important part, which is the logistics of this whole learning group. Again, it looks that way. This is like the continuity of the last year's event series. The idea is that I'm gonna do like one meetup on different zero knowledge topics each month. It might happen that only 2 months, but so well, basically at the beginning I was considering if I can do it each month or rather in 2 months. But basically there's enough topic to cover, like, I mean, 12 meetup series during this year. So it's a bit questionable if I can prepare, but I mean, let's just hope the best. It might happen that few topics will be more boring, but I will try to plan one such a session each month. The idea is similar that it was last time. One difference is that I'm gonna involve more guest lecturers because it might happen that it's just boring if I do this presentation on my own. So basically, if you know any zero knowledge experts or application developers or programmers who is keen on like doing a lecture here, then they're more than welcome. Basically, again, it's just open to everybody. It's like on a community basis. It's just there's one rule. It should be that like zero knowledge proofs, on topics on zero knowledge proofs. Basically, the idea is that we're gonna have like this one session, which is like 1 hour practical presentation from my side. It's always a little bit questionable if we have like much time for discussions, but basically we are having like a Discord channel, and then we can discuss things practically, not offline, but not in the meetup, but basically practically in a chat in the Discord channel. The idea is for this year, I'm gonna structure a little bit like in a similar way than last year. So we're gonna start with like more theoretical things. Not quite sure if you have like lookup tables, but basically we're gonna start with zero-knowledge variations, which are STARKs and FRI. We might as well have something more on a more theoretical basis, like recursive SNARKs. And then we will continue in the middle of the year with zero-knowledge programmings and platforms. Last year we covered Circum and Noir as platform or zero-knowledge platforms. So this year I'm probably gonna cover like Zinc and ZK Sync or Cairo or perhaps Leo as zero-knowledge programming platform and languages as well. And at the end of the year or at the last part of the year, we're gonna continue with like zero-knowledge applications. It's like one idea is like zero-knowledge bridges, zero-knowledge virtual machines, perhaps zero-knowledge identity, or like if you think of like verifiable credentials and the presentations of verifiable credentials, that might be like an application, or voting, or there might be like privacy topics with like shielded transactions. So actually, that's the idea for this year. But basically, so things are pretty much flexible. So if you have like ideas that you are keen to have like one lecture, then we can likely discuss in the Discord channel. Practically, I would say I myself not a mathematician. I'm more like an application developer. So I'm more comfortable with like programming and application fields or application areas. If it's something very deep theoretical, it's a bit questionable if I can prepare. But again, if you have any ideas or any specific zero-knowledge topic that you're interested in, just feel free to chat in the Discord channel. So to continue, we got some coordination for this learning group. And first, we have like a Discord channel. It looks that way that Linux Foundation Decentralized Trust has a Discord channel. If you are not a member, then you can get a membership just simple Googling, just Google LFDT Linux Foundation Decentralized Trust, and then you should Google like Discord channel invitation. And you will have an invitation link. And if you have the invitation link, then you can be easily part of this Linux Foundation Decentralized Trust Discord channel. There are a lot of things here, but practically we are somewhere here under communities, and under communities there's like a zero-knowledge learning group. So practically I'm posting everything here, and then again, if you have like any ideas for like a guest lecturer or any ideas for a topic that you are keen to hear, then just just feel free to post here. So that's one thing. Then we are having these meetups on meetup.com, of course. It's not geographically, focused basically. So basically these meetups will be announced practically on all like Linux Foundation, Decentralized Trust meetup groups. So you will find them practically everywhere. And an important things, we have like a repository for everything, which is under Linux Foundation Decentralized Trust Labs. You will find under ZK Learning Group. And you find the course from last year here fully. So basically, you will find the syllabus for 2025. So from February, you find all the slideshows, all the recordings, or the presentations, all the links and literatures. There are sometimes quizzes. There are sometimes application challenges. So basically everything is here. And then we will continue this in 2026. So practically similarly as before, you will find here the slideshows, you will find here the recordings, you will find here the meetups. If there's code or quizzes, then you will find here actually the challenges, and then you will find some solution here as well, basically, and links and literatures as well. So for instance, it's not just one page. So if you just go up and then take a look, there are some example codes, for instance, for Circum and Noir, or documentations and PDFs. So you will find practically everything in this repository. Okay, so that's like the logistic for this course. And then after the logistic, let me just start with like zero knowledge proofs. And let me just have this first slide. It's probably boring sometimes, but if you're new in the field, it might not so be boring. But let me just summarize it very briefly. So practically, if we think of like zero knowledge proofs, then we usually have like two roles, Alice and Bob. We usually say a prover and the verifier. And basically, a prover tries to prove practically a fact. Like Alice tries to prove like a fact for Bob in a way that Bob gonna be convinced that this fact is true and it is known by Alice. And if that's zero knowledge, then it's gonna happening in a way that Bob will not know the fact itself. So very simple example. Let me just imagine that Alice claims that she knows a pre-image of a hash function, and she creates a proof for Bob that she really knows like a pre-image of a hash function, and Bob gonna be convinced that Alice really knows this pre-image of a hash function, but in a way that Bob will not know simply the pre-image of this hash function. So that's like a zero knowledge proof, and there are like different variations. So usually we can think of like interactive proofs. If that's an interactive proof, there are like many iterations between Bob and Alice, between the prover and the verifier. If that's non-interactive, then there's just one proof, and Bob gonna be either convinced or not convinced that Alice really knows this fact. Another example is here, which is like Sudoku. So practically you can imagine a game in which Alice tries to convince Bob that she really knows like the solution of a certain Sudoku puzzle in a way that Bob gonna be convinced that Alice really knows the solution of this Sudoku puzzle, but in a way that Bob will not know the solution itself. So that's like zero knowledge proof. Um, uh, to be like a little bit more specific, if we think of like zero knowledge proofs, usually we have something which is like a computation model. So you can imagine that we can have like many domain problems, like that I mentioned, that was Sudoku or hash function, that but there can be like many other things, many other domain problems here. So we express these domain problems with the help of a computation. And this computation might be a little bit like specific. Usually it's like an arithmetic circuit or something abstract, but you can imagine it's practically like a circuit. So let me imagine that's a circuit that has some input public variables, some input private variables. We can call these private input variables as witnesses as well. And then it produces either true or false, or it can have like an output practically. And then for Alice and Bob, to be like more precise, we usually think of like a prover algorithm and the verification algorithm. And the prover algorithm takes like the public input and the private input and creates a proof. And the verifier gets like the public input, the proof itself. The verifier doesn't get like the private input, and either accepts or rejects that proof. So if you think of like the two previous examples, then like W, which is like the private input, that was like the solution of the Sudoku puzzle, or that was like the pre-image of the hash function. Okay, and we need some properties for our zero knowledge proofs. Basically, it should be like small. Small is usually succinct, or we call it succinct. It means small in size and easy to verify. So basically, it's not something that like we give the whole solution and the whole problem to Bob to check, but it should be really something small to verify, and both in size and in time as well. We have some other properties like completeness and knowledge sound. So complete is something that if Alice creates like a proof, I mean, if she really knows like the solution of the Sudoku puzzle and creates a proof, then basically Bob gonna accept it with very high probability. And there's like the other direction as well, like if Bob accepts practically a proof from Alice, then Alice really knows like a fact, really knows like the solution of the Sudoku puzzle. So these are like the two directions that should be hold, that should be true. And we have something which is zero knowledge, of course. It might be surprising. We speak of like zero knowledge proofs, but basically we do not necessarily need zero knowledge, zero knowledge property. Zero knowledge property is actually that there's nothing revealed from the hidden fact. I mean, to Bob, basically. That's like zero knowledge. But for a lot of applications, we do not really need like zero knowledge because we can just exploit the situation that there's like a complex computation or complex problem, and there's a small proof that this complex computation, this complex domain problem was solved in a correct way. And we just prove practically, we just check the proof that the complex computation was executed in a correct way. So we do not necessarily need like the zero knowledgeness for a lot of applications. Like one example is like for rollups, for blockchain rollups. Zero knowledge proof is zero knowledge. The zero knowledge of the zero knowledge proofs is not necessarily required. So having that, we get like two systems. I mean, actually, we get more than two systems. But what I'm doing is I'm just comparing SNARK with STARK. And SNARK is, which is we call succinct non-interactive argument of knowledge. And STARK is scalable transparent argument of knowledge. So what's the difference and similarities? Let me just start from the end. In both cases, we get like argument of knowledge. Argument of knowledge that's practically the same. Alice, I mean, that's the fact which is known by the prover, which is known by Alice. So that's the fact of the preimage of the hash function, or that's the fact of the solution of the Sudoku puzzle. Again, argument of knowledge is the fact that Alice knows a fact, and then there's gonna be a proof based on that fact and some computation. Okay. So first, SNARK is succinct. Succinct means small. Small in size and fast to verify. I mean, the proof size and the verification time is pretty fast. That's one property. It's usually logarithmic, but actually there's like systems like the Gross16 where the proof is constant. It's pretty remarkable that something can be done, but basically there's a way like with Gross16 to create like a constant size proof. So basically succinct is really small. However, the problem is that there's no constraint for proof generation of a SNARK. So like the proof generation might be actually pretty intensive. If you think of like one application, there was like one zero knowledge application, which was, I think it was named the Dark Forest. And it worked that way that it was like a blockchain-based game, if I'm not mistaken. And then basically they had like a lot of JavaScripts, and then some moves of the games were actually done on the front end in JavaScript applications. But to make the whole system more trusted, these steps on the front end side were supported by zero knowledge proofs. So if you think of such an application, then basically the zero knowledge proof itself, or a SNARK proof, is generated on the front end side, which means practically that your computation power in a browser with JavaScript is very, very limited. So it might be a problem that, I mean, if you think of SNARK, basically the computation might be, sometimes extreme. Then SNARK says like non-interactive. So non-interactive means we just want to create one proof from the prover, from Alice, and we verify either accepts or not accept. Basically, that's what we like practically a blockchain application. So on the other hand, STARK, in STARK, we have something which call scalable. It doesn't actually mean that it's not succinct. It's just, I don't know, for some marketing reasons, we have like other terminology a little bit. Basically, the idea is that the proof is still small, but it's not necessarily so small at SNARK. So like the verification time is polar logarithmic. Again, if you think of SNARK, the proof sizes and the verification time is sometimes just constant. So basically, polylogarithmic is like slower in a sense. And then basically we have one constraint for the proof generation. So the proof generation is usually like something a little bit like quasi-linear. So it's like something with log squared practically. So there's like limit for proof generation as well. And perhaps for scalable, sometimes it is not interpreted, but it is interpreted. I would interpret from a practical point of view this property to scalable as well. So in SNARK, usually we have like another computation model, which is like a circuit, which is not necessary, can be implemented very efficiently or extended very efficiently. But basically in SNARK, we have like a different computation model. It's more like a virtual machine, which can be used for a lot of different use cases, very flexible. So I would say scalable might mean as well that the computation model itself is more scalable. Another difference is setup, trusted setup. So if you think of like this slide, usually in the arithmetic circuit, in the proving and verification, we have like one third property, which is like a trusted setup. And it looks that way that most SNARK algorithms requires like a trusted setup, which has like many different problems. We're gonna cover them in like 2 slides. The point is for stars that they do not need like trusted setup. So they are transparent, means no trusted setup. So Stark might be interactive or non-interactive. Usually we like them non-interactive in blockchain applications, but there's like, way to using them practically interactive in an interactive way as well. It's just there's like one transformation which helps transforming some of the interactive proofs to non-interactives. It's like the Fiat-Shamir transformation basically. Okay. So let me take an other look and let me just try to compare them from another point of view. Again, I'm just throwing slides during this presentation, highlighting the differences, a little bit the differences between SNARK and STARK systems. Again, from a high level perspective, we take a little bit the theory, or we take a look into the theory a little bit next time. So that's like another perspective. It's like an algorithmic comparison of different systems. And then if you think of, we can have like, different Zenoid systems. And then we can compare them based on different properties, like practical properties. So usually what we think of, we can have like the size of the proof, which is important because if you think of in like most blockchain applications, you want to write your proof into the blockchain in an immutable way, which is, of course, it means that basically you need a storage in the blockchain. And then, in most of the application, most of the blockchain applications, the two extremely costly things are one is the storing anything in the blockchain. The second is computing anything with the blockchain. So size matters and verification time matters as well. So in terms of size, gross 16 is the smallest. It's like a constant. In verifications time, again, gross 16 is the fastest. We have something which is a setup, and then again it's like the parameters at the end, at the beginning of the setup. And then the problem is, of course, which is not very much practical for row 16, is that we have one trusted setup per circuit, which is like, which might be pretty problematic in some cases. And then usually one other parameter is like post-quantum readiness. Well, it's gross 16 based on kind of an not elliptic curve, but like bilinear pairing, if I'm not mistaken. and then it's not post-quantum ready, so practically it might be cracked by quantum computers if they come. Anyway, Gross 16 is a SNARK system, and then so for the there could be like one more column here, which is the proving not the proving time, but the proof creation time. And then it's pretty hard to estimate because in Gross 16 we just implement basically a circuit, and then the proof creation time depends on the size of the circuit as well, but it can be basically like big. Another system is like Plonk-Marlin, which has like different characteristics, but basically the size of the proof is still small, the verification time is still small. We have universal setup per circuit, and it's still not post-quantum ready. We got like Bulletproof, it's like a little bit like different systems, so I would not include it it's just on the slide. But basically comparing to like Gross 16 and Plonk and Marlin, which are like classical SNARK systems, we can have like STARK, and then if you think of like STARK, then basically the size of the proof is already not constant, but like something which is not even simply logarithmic, but like logarithmic to the squared. And then that's the same for verification time as well. So these are like these advantages. Two advantages, though. On the one hand, the setup is transparent, so you don't need like anything like precompiled parameters or cryptographic material, and it's post-quantum ready. The reason is for that because it's based on like hash functions and Merkle trees, and hash functions and Merkle trees are actually more quantum ready than like, for instance, elliptic curve operations. So just to have one slide. So I mentioned trusted setup in SNARK, and then trusted setup is of course a problem. Just for the completeness, it's important to know that there's a workaround for trusted setup, which is works in some way. So the problem is in SNARK systems that basically you need like a setup for the proof system, and then there might be two problems with this setup. So basically, on the one hand, people can cheat, like basically creating this setup. And then if they cheat, then basically they can prove certain facts that are not true or not known by the prover, for instance. And another problem is that basically there are some parameters, like some random parameters that are used during this setup that should be deleted. Otherwise, if they are leaked, then basically, so if they are hacked and leaked, then basically, if a hacker takes or gets these parameters, then basically a hacker can again prove things that are not correct. In a sense, more specifically, it means that like, I mean, if we have like Alice and Bob here, and we have a trusted setup, and basically a trusted setup is somehow, we usually call certain parameters of this trusted setup as toxic waste. So if this toxic waste is not handled correctly, or if that's leaked to a hacker, then basically a hacker might create proofs on facts that the hacker doesn't know. So like, we have like the classical hacker in this situation is Mallory, and we're gonna have here somewhere Mallory. So if Mallory gets this trusted setup or hacks this trusted setup somehow, then for instance, Mallory can create a proof to Bob that he knows like the fact, the solution of this Sudoku puzzle, but actually he doesn't know the solution of this Sudoku puzzle. He just simply hacked like the setup parameters of the system. So that's like the problem of trusted setup. And again, there are situations where we need like pair computation model. There are situations where we need this just once, but nevertheless, I mean, anyway, it's not something which is good. I mean, it's clearly like a disadvantage of these SNARK systems. There's a workaround basically that you can use even if you have SNARK, which is like, it is called the power of tau ceremony. It's practically a multi-party computation to generate these setup parameters and these setups for ZK SNARKs. It looks that way, that there are multiply actors or people creating these parameters, contributing in this randomness, and basically if these actors act really independently from each other, then the resulting parameters remain secure and confidential. Depending on the used algorithm, there might be, like, even if like one participant acts honestly, then basically the result can be secure and confidential. Okay, so that's like the power of Tau. So there might be some workaround even if we have like trusted setup, but basically, yeah, it has some limitations. And in Stark, we just don't need it, basically. Okay, so that's like one difference. The second one, I would say, I have one slide. Again, it's a little bit like an introductory session at the beginning of this year. I usually cover this topic, but at the moment I just created one separate slide on that. So basically, from an application programming perspective, there's a flow how we can implement like such a zero-knowledge application. And it usually looks that way, that we don't create like arithmetic circuits or something similar, but we usually use like one higher level language. So basically we have a domain, which is like the computation. Again, computation, or the domain was like the Sudoku puzzle or the hash function. And we try to somehow express this computation in a high level language, in a high level zero-knowledge language. That is usually like kind of a specific domain specific language. But anyway, we usually have like high level programs, and as an application developer or even cryptographer, we just try to emphasize or try to express our problems in this high level language, in this high level computational model. And the next step, which is done automatically by the proof system or proof platforms, is the so-called arithmetization. So as the next step, usually this computation is compiled into something which is like, more abstract. It's still not fully mathematical, but it's like more abstract. And that's usually something which is like an arithmetic constraint system. And this arithmetic constraints system, basically something which is like equations on finite fields. So from a mathematical point of view, these are equations on finite fields, and these are like constraints to a solution, what or how like a valid computation looks like. And if you have this arithmetic system and practically like the equations, then we can have some further compilation, and then basically we have something which is like polynomials, and based on the polynomials we have something which is like a polynomial interactive oracle proof, and basically these polynomial interactive oracle proofs are extended, or another element is added, which is like polynomial commitments. And if you have both the polynomials, we just build that like interactive oracle proofs and commitments as well, then basically we have our full cryptographic proof system. So these are like the general steps which can be considered at like a zero-knowledge programming. And of course, there are like different high-level computational languages. There are like different arithmetic constraint systems, different polynomial IOPs, different polynomial commitments. And of course, at the end, there are like different tools for based on different implementation and theoretical considerations to use this whole zero-knowledge stack. So again, it's like one general slide on the high level flow of zero-knowledge programming. And we covered last year, we have something which is like an so-called arithmetic circuit in SNARK. It's an abstract representation of computation, which looks that way. It's like an intermediate representation between the high-level computational model and then the lower-level like polynomials. It looks that way. It's like a directed acyclic graph, and then we have some. Of course, it's like on a finite fields, so we have some inputs. Basically, we have some gates. These gates are wired or connected to each other, and usually we have something which is addition and multiplication. And then we have some inputs at the beginning that can be like public and private. And then basically we have, of course, one output, which can be like, I mean, either a real output or basically we can just compile to a predicate. So if that's a predicate, then it's either 0 or 1. And so, for instance, if we have a problem that, hey, our domain problem is to express that we know like the pre-image of a hash function, then basically this hash function can be expressed with such an arithmetic circuit, for example. So one of the problem that, I mean, even if you program on a high level, despite programming in such arithmetic circuits is like difficult, because I mean we can express pretty well like one problem, but that can be like very strongly like domain specific. So if you just want to extend that problem to something else, then it might be different. It can be complicated. But again, that's like SNARK. And the point is that in SNARKs, we have something else as an intermediate, I would say, arithmetic representation or intermediate representation. And that's what we call as arithmetic intermediate representation. And it looks more like as a computation, basically, as a computation of a virtual machine. So we got something which are like registers. Again, so at the end, these are all polynomials on finite fields, are all going to be polynomials on finite fields. So let me just not imagine like real registers of a CPU, but let me just imagine something which are like abstract registers taking values from finite fields. And the idea of the computation model is that we got like registers or values in our registers, and we have some computation, and then basically based on the computation, we're gonna have like the new values of our register, and then there are some more computations, and we have like the new values of our register, and so on and so forth. So basically, we have like a trace of computation of our register. And that's what we just try to express with or abstract more with like polynomials. So basically, we will just introduce somehow like trace transition functions. And then trace transition functions somehow makes like constraints how this computation can be done or should not be carried out. And then basically each such a step will be somehow expressed by state transition functions that can be at the end like something which is like an algebraic execution trace. So these are like, again, like computational constraints or transition constraints. And then based on these functions, we create our polynomials. And then these polynomials are gonna be like the basis for our zero-knowledge proofs on a more abstract level. Again, I would just go back and then have this slide again. We have something which is a high-level computation. And then this one is like arithmetic constraint system. So we are somewhere here. We just try to have something intermediate, which can be abstracted to polynomials. And if we have polynomials, then basically we can have like the mathematical magic of both polynomial IOPs and polynomial commitments, and we have our proofs. But the point is to have our computation to compile somehow into such polynomials. And again, SNARKs having usually this like arithmetic circuit representation, and STARKs having something which is like more virtual machine native, which is an arithmetic intermediate representation. And actually one reason for that we do not need like pre-processing step in STARK is this representation. So this can be like Basically, we just need like the input registers and like the state transition functions, and that can be already given to like both the prover and the verifier. As opposed to Stark, in Stark we usually need like this pre-processing step, is just because that's a step which somehow compiles this arithmetic circuit that might be pretty big. Okay. So, but again, that's like one idea and one comparison. I would have again, that's like again a general slide. It's like construction. We just going to go one level deeper. So basically, if we have our polynomials independently, if we got from like the arithmetic intermediate representation or arithmetic circuit, we can create like our proof. And for creating our proof, usually we use like two abstract mathematical objects. One is like a functional commitment scheme. Functional commitment scheme somehow commits practically one function from the prover to the verifier, and the verifier can basically ask the prover to open this committed function at one point, and basically the prover gonna send a proof that basically the certain point is evaluated to a certain value, and then the correct function was committed as well. It's a little bit abstract, but again, we are just plunging a little bit into the mathematical depths. So that's like functional commitment, and based on functional commitments, we just create like interactive oracle proof, which is like an extension. So basically, we have not just one function committed, but many functions committed, and basically we can just ask the verifier can ask basically the prover to open these committed functions at many different points, and based on that we have like an interactive proof, and there's a way of doing this interactive proof to a non-interactive one, which is like a Fiat-Shamir transformation. It's basically if a protocol has like some I would say coin-based randomness, then it can be done to non-interactive, like with using hash values. Again, I'm not gonna go more into the details. It's just important to remember that on a very deep level, we're gonna have something which is like functional commitment, interactive oracle proof, and some Fiat-Shamir transformation, and that's what we need for our proof. And the point is that we are having like different implementations, even on the deep theoretical level. So we can have like different polynomial IOPs, and we can have like different polynomial commitment schemes. So it's like interactive oracle proofs can be like multi-prover, constant rounds, like interactive proofs, and there are like many different realization. And there are polynomial commitment schemes as well, which work differently, like based on different mathematical assumptions. Like we can have like the KZG, which is like on pairing, bulletproof is on discrete logarithm, and then basically we have something which is in Stark, we have one specific algorithm that is used for both for actually as a polynomial IOP and indirectly for polynomial commitment scheme as well. And that's like FRI, that's fast read Solomon interactive oracle proof of proximity. And the main idea is, for instance, if you remember in the third slide, so we spoke of like quantum resistance and non-quantum resistance. So for instance, quantum resistance comes from the polynomial commitment scheme. Because the point is that usually polynomial IOP is something which is called like an information theoretical object. So basically, it's not dependent on the computation power of the attacker. But polynomial commitments are different. So basically, they are more cryptographic objects. So basically, there's always like an assumption how much power basically an attacker, how much computation power an attacker has. And the problem is that like in pairing and discrete logarithm. If there's like a quantum attacker, then basically these algorithms can be hacked. But the point is, for like STARKs, and again, the algorithm which is used behind is FRI, Fast-Reed-Solomon Interactive Oracle Proof of Proximity. It uses hashes and Merkle trees, and hashes and Merkle trees are difficult to crack even with quantum computers as well. So that's practically what gives like quantum resistance or more quantum resistance for these proofs. Okay, and one slide, platforms. So basically, if you think of SNARKs or STARKs, you have like different, I mean, this one is more from a practical point of view, not from the algorithmic one. So we can have like different platforms and different like high-level languages, mostly like domain-specific languages, programming these environments. So in SNARK, we have something which is like Circum, Noir, Socrates, Leo. This should be like Leo, Halo 2. These are like languages and well, actually like proving platforms. I mean, combined with proving platforms as well. But we have like, like bigger application platforms as well, like Aztec, like ZK Syncs, like Aleo. The point is that in Stark, we still do not have so many frameworks, languages, or platforms, but probably that's gonna be evolved pretty fast. So we have languages like Cairo, and we have like platforms like StarkNet, StarkX, for instance, are examples. So that was the hardcore part of my presentation. Usually I have one challenge. Well, basically, as this one was pretty much high level, I do not really have like challenge here. So I would say if you can think of like experiment with any kind of Stark system on your own, well, that would be like a challenge. And as usual, I have some links, resources, and literatures. So if you need like further reading on this topic, these are usually not the hardcore academic literature what I have here, but it's really like the like the basics and starting point of like Stark at the moment. So that was my presentation for today, and well, I would say we have a few minutes. So if you have like any questions, I will try to answer them. Again, it's just think of it, this is a learning group, so I would not say that I'm basically the biggest expert in this topic. It's just, I mean, the idea is that we learn this topic together, so I might not be able to answer all of your questions. But again, so if you miss something, then you can just basically drop a message in the Discord channel list. So I'm just reading actually the questions in the meeting chat. So there's one question. If it is recorded, yes, it is recorded. You will find the recording basically in the YouTube channel of Linux Foundation Decentralized Trust. I will post it here as well, basically in this Discord channel. And as far as I know, it will be shared by email as well to you. So both the recording and the slideshow will be shared. But one other thing, so I'm just sharing this repository. So again, basically, I would say a good starting point is always using this repository. So if you just save it, basically, it looks that way. And we're gonna have like, I mean, the slideshow presentation, I mean, the link to the slideshow is already here. Recording gonna be here as well, and then some code challenges, links and literatures. I mean, that can be a good starting point, but basically, as I mentioned, it's gonna be emailed to you as well. So one other question is if we do concrete examples end to end, like in Cairo, proving some common types of statements. The slides are abstract. I know it's abstract. It's abstract even for me as well. So let me just go back to the first logistical slide. So again, perhaps what I would say, what I did last year. Again, the idea was basically we started in February with the introduction. We covered in March and April some theory, like polynomial commitments and interactive oracle proofs. So that was the first part of the year, or first third of the year, which focused more on theory. And then in the middle of the year, we focused on programming. So we had like programming exercises in two different domain-specific languages. One was Circum, so we had like two meetups. One was basics of Circums, and then the second was like more advanced Circum. I wouldn't say it was absolutely advanced, but it was more advanced. So we did like coding exercises. And then we covered with Noir. So I had like one presentation on the basics of Noir. Practically what we do is like having like a basic hello world in Noir. And then there was like one more session which was like more abstract, well, not more abstract, but more advanced Noir programming. Again, I would not say it was like fully professional, but we just covered more programming structures and we created more complicated proofs as well. And at the end, we had like applications. So it was more like in an application layer again, how like proof of reserve, proof of solvency work, how decentralized AI works, how rollups works, and so on and so on, and with ZK login. So that's the idea for this year as well. I know it's hard at the beginning, but I'm covering like this one, and the next one probably like even more theoretical. I'm gonna cover FRI, and perhaps we will have like one more theoretical session at the end. So we will have like like three different like theoretical presentations. And in the middle of the year, we're gonna do like programming. So we start with like programming languages like with Cairo, and then we create like a hello world, or we create like a meetup on a hello world of Cairo, where we create something very simple, just having like one proof and one verification. And we're gonna have like a second meetup, or a second meetup as well, with like more advanced Cairo concepts, where we create something more complicated. And we probably have like the same for Zinc or ZK Sync, or if you wish, I mean, we can have like Leo. And like from September, we will have like applications. So we go more into the details, how ZK bridges virtual machines, verifiable credential, identity, or voting work. So that's the idea. I know it's a little bit like abstract. It's just, I mean, my experience is that it's just better to focus more like at the beginning, like on a theoretical basis in one block, and then on programming in one block, and in application in one block. Because if I just keep switching among these topics, then it's just even more confusing. So just imagine we have like one Cairo presentation and one FRI. I think it's gonna be like even more difficult. Uh, so the next question for the challenges, yes. So the challenges are actually easy, but I mean, again, we can likely discuss basically like in the Discord channel. So the challenges were last year like, I mean, I don't know, create something with hello world in Circum, for instance, in the programming part. Let me just take a look. What was it? Basics of Circum, and then so like one challenge was, I mean, we just had something which is like a hello world of Circum, and then the programming or developer challenge was just create like like a Fibonacci series with one private input and one public input, and then create a proof on that. That was like the developer challenge. It was not so difficult. Usually people are not very keen on solving these challenges, but anyway. And then so after a few weeks, I created like a solution for that as well. So you can find basically like one very simple solution for this Fibonacci is here. It's again, it's nothing nothing very difficult. It's just, so it's not like building up a full application. It's just a little bit practicing what was basically doing this presentation. But again, we can likely discuss things in the Discord channel. So we have like 2 minutes left. So are there any questions or other questions? Again, if you have like further questions later on, just feel free to join to the Discord channel and then ask the questions here in Zero Knowledge Learning group. I will try to answer every question. If it's too theoretical, it might be too abstract for me, but nevertheless, I will give a shot. Okay, so if there's no more questions, then that was for today, and that was like the kickoff of the year. So thank you very much for the attention, and then see you next month.